On paper, German and American heavy machinery look unstoppable, engineered by two industrial giants with decades of experience and global dominance. But once these machines leave the showroom and face mud, dust, deadlines, and human error, something unexpected happens. Design philosophies collide. Strength becomes a weakness. Precision turns into a risk. This is not a story about which country builds better machines. It is about why machines built with completely different assumptions behave so differently when the real world stops playing by the rules. From construction sites to disaster zones and battlefields, small design choices lead to massive consequences. Some machines shut down to protect themselves. Others keep going until something breaks. The difference is shocking, and it matters far more than most people realize. Power versus practicality. Why German and American machines are built to fight different battles. The difference between German and American heavy machinery is not accidental. It is the result of history, geography, war, regulation, and industrial priorities that diverged sharply after World War II from 1945 to 1949. While both nations produced some of the most powerful machines on Earth, they were designed to solve very different problems. And those differences continue to cause conflict and controversy in modern construction, mining, and military logistics. In Germany, heavy machinery design grew out of limited land, dense infrastructure, and strict regulations. Companies like Liebherr, founded in 1949, and Eman, established in 1758, were forced to prioritize efficiency, compact engineering, and precision. German engineers worked within narrow European road networks, strict axle weight limits, and fuel efficiency laws that became increasingly restrictive from 1970 to 1980. As a result, German machines emphasize high torque at lower engine sizes, advanced hydraulic systems, and modular components that maximize output without excessive bulk. In contrast, American heavy machinery was shaped by scale. The United States had vast open terrain, cheaper fuel, and fewer transportation constraints, especially from 1950 to 1980 during the post-war industrial boom. Companies like Caterpillar, founded in 1925, John Deere, established in 1837, and Komatsu America, which expanded heavily after 1970, focused on raw horsepower, mechanical simplicity, and durability over long distances. American machines were built to move massive loads across deserts, plains, and mining sites where space was not a limiting factor. This philosophical divide became especially visible during the Cold War from 1947 to 1991. Germany, divided into East and West, had to rebuild rapidly while conserving resources. West Germany invested heavily in precision manufacturing, influenced by NATO logistics standards and European interoperability. American machinery, meanwhile, supported large-scale infrastructure projects such as the Interstate Highway System, launched in 1956, which required bulldozers, graders, and excavators capable of continuous heavy operation with minimal downtime. Power, in the American sense, meant bigger engines and simpler systems. A Caterpillar D9 bulldozer, introduced in 1954, became a symbol of brute force, using massive displacement engines and reinforced frames designed to withstand extreme abuse. German equivalents from Liebherr or Mercedes-Benz emphasized hydraulic efficiency, operator control, and fuel economy. This contrast fueled long-standing debates in global markets about whether brute strength or optimized efficiency delivers better long-term value. Another major point of conflict lies in labor and maintenance philosophy from 1960 to 1990. German machinery was designed with the assumption of highly trained operators and certified technicians, supported by formal service networks and manufacturer-approved diagnostics. This approach improved reliability in controlled environments, but reduced flexibility in the field. American equipment, by comparison, was engineered for fast, improvised repairs using standardized parts and basic tools. In international projects from 1985 to 2005, American machines often stayed operational despite damage, while German machines delivered peak performance only when proper maintenance conditions were met. Critics of German machinery argue that precision comes at a cost. Advanced electronics, proprietary components, and complex diagnostics can turn minor failures into expensive shutdowns. By 2000 to 2010, many German machines relied heavily on computer-controlled systems to comply with European Union emissions and safety standards. When these systems fail in remote or hostile environments, repairs can be slow, costly, and dependent on specialized technicians. On the other hand, American machines face criticism for inefficiency. Larger engines consume more fuel, generate higher emissions, and often struggle to meet international environmental regulations introduced after 1997, following the Kyoto Protocol. These challenges have limited export potential, forcing manufacturers to redesign engines, reduce emissions, or shift production strategies. Military logistics further expose the divide. During operations in Iraq from 2003 to 2011, American forces relied heavily on U.S.-built heavy equipment for rapid base construction and route clearance. These machines performed reliably under extreme stress, but demanded constant fuel supply. German military engineers, operating under NATO constraints, favored smaller, more efficient equipment that could be transported quickly and sustained with fewer resources. Ultimately, German and American heavy machinery are not competing versions of the same idea. They are responses to different realities. German machines are built to win battles against regulation, space limitations, and efficiency demands. American machines are built to overpower terrain, distance, and time. The controversy emerges when one system is forced into the other's environment, where precision may fail under chaos and brute force may collapse under constraint. Engineering, pride, or engineering problems, the philosophy divide. At the heart of the conflict between German and American heavy machinery lies a deeper issue: engineering pride. What one side calls superior design, the other often sees as unnecessary complication or dangerous oversimplification. This philosophical divide did not emerge overnight. It evolved through decades of industrial competition, military pressure, and economic reality, especially from 1945 to 1990, when both nations rebuilt, expanded, and defended their influence on a global scale. German engineering culture has long emphasized precision, optimization, and theoretical efficiency. Rooted in formal technical education systems dating back to the 19th century, German engineers are trained to design machines that perform at peak efficiency within defined parameters. After World War II from 1945 to 1949, this mindset intensified. Germany faced material shortages, destroyed infrastructure, and strict post-war controls. Engineering excellence became not just a goal, but a necessity. Machines had to do more with less, using tighter tolerances and smarter systems rather than sheer size. This philosophy shaped companies such as Liebherr, Bosch Rexroth, and Mercedes-Benz, which focused on tightly integrated systems, advanced hydraulics, and finely tuned engines. From 1970 to 1990, as European environmental and safety regulations expanded, German manufacturers leaned further into complex solutions. Electronic engine management, precision sensors, and automated controls were not luxuries. They were tools to survive within regulatory constraints. For German engineers, complexity was not a flaw. It was proof of mastery and discipline. However, this pride in complexity has drawn criticism. In real-world conditions, especially outside Europe, highly optimized systems can become fragile. When a single sensor fails or software malfunctions, an entire machine can shut down. Field operators in Africa, the Middle East, and parts of Asia reported issues from 1995 to 2010, where German-built equipment required specialized diagnostic tools and factory-trained technicians. What German engineers viewed as elegant design, operators often experienced as downtime, supply delays, and lost revenue. American engineering philosophy developed along a different path. In the United States, practicality and results often outweighed theoretical perfection. From 1950 to 1980, American industry expanded rapidly, driven by mining, oil extraction, highway construction, and large-scale agriculture. Machines were expected to work long hours, far from service centers, often in extreme heat, dust, or freezing conditions. Simplicity was not ignorance. It was survival in hostile environments. Manufacturers like Caterpillar, John Deere, and Case prioritized mechanical robustness and ease of repair. Components were oversized, tolerances were forgiving, and systems were designed to fail gradually rather than catastrophically. An American bulldozer losing partial function could often keep working. A German machine encountering a system fault might shut down entirely. This difference became a major point of contention in international bidding processes from 1980 to 2000, especially in developing regions. Yet, American engineering pride has its own problems. Oversized engines and simplified systems often sacrifice efficiency. Higher fuel consumption, increased emissions, and heavier frames became liabilities as global regulations tightened after 1997, following the Kyoto Protocol. From 2000 to 2010, American manufacturers were criticized for being slow to adapt, relying on legacy engine designs that struggled to meet new standards without costly redesigns. The divide is also cultural. German engineers often design for ideal operating conditions, assuming trained operators, scheduled maintenance, and controlled environments. American engineers design for misuse, operator error, and unpredictable conditions. Neither approach is inherently superior, but each reflects assumptions that can fail when exported globally. This philosophical conflict became especially visible in joint ventures and multinational projects from 2000 to 2015. Hybrid machines combining German systems with American frames sometimes suffered from compatibility issues. Precision electronics clashed with rough-use environments, creating reliability problems neither side fully anticipated. Engineering pride on both sides often delayed compromise, turning cooperation into competition. Ultimately, the debate is not about intelligence or capability. German engineers are not too smart, and American engineers are not too simple. The problem arises when pride hardens into inflexibility. When design philosophy becomes ideology, machines stop serving operators and start serving egos. The philosophy divide is not just technical, it is strategic. It influences procurement decisions, military planning, and long-term infrastructure investment. And in the harsh reality of construction sites, battlefields, and disaster zones, philosophy is tested not by theory, but by failure. Overbuilt or overcomplicated, when precision becomes a liability. The debate over German and American heavy machinery reaches a critical point when precision stops being an advantage and starts becoming a liability. From the outside, German machines are often praised as engineering masterpieces, while American machines are labeled as crude but tough. However, real-world operations from 1980 to 2020 reveal a more complicated truth. Machines that are over-engineered can fail just as dramatically as those that are under-refined. German manufacturers built their reputation on precision after World War II from 1945 to 1949, when efficiency was not optional but essential. Limited resources, destroyed factories, and strict oversight forced German engineers to extract maximum performance from minimal material. Over time, this evolved into a design culture that prioritized tight tolerances, integrated systems, and highly optimized components. By 1970 to 1990, German heavy machinery increasingly relied on advanced hydraulics, electronic controls, and interdependent subsystems designed to function perfectly under ideal conditions. This approach produced impressive results in controlled environments. German excavators, cranes, and loaders delivered superior fuel efficiency, smoother operation, and higher output per unit of engine displacement. In regulated European construction sites, where operators are certified and maintenance schedules are strictly enforced, this precision translated into measurable gains. But outside those conditions, the same precision often became a weakness. The problem lies in system dependency. In many German machines produced from 1995 to 2015, a single failed sensor, calibration error, or software fault could disable the entire unit. Safety interlocks, emissions controls, and automated shutdown protocols were designed to protect the machine and meet regulatory requirements. In practice, these systems frequently halted operations in remote or harsh environments where immediate repair was impossible. Precision created fragility. Field reports from mining and infrastructure projects in Africa, South America, and the Middle East during 2000 to 2018 consistently highlighted this issue. Operators described machines that were mechanically sound but electronically immobilized. Replacement parts were proprietary. Diagnostics required manufacturer-specific tools, and repairs depended on factory-trained technicians. Downtime, not mechanical failure, became the primary risk. American heavy machinery followed a different trajectory. From 1950 to 1980, U.S. manufacturers designed equipment for vast distances, limited oversight, and unpredictable conditions. Overbuilding was intentional. Frames were heavier than necessary. Engines were larger than efficient, and mechanical systems were favored over electronic ones. This resulted in machines that tolerated abuse, poor maintenance, and operator error. Critics often describe American machines as inefficient or outdated, and in many cases that criticism is valid. Excessive weight increases fuel consumption. Larger engines generate higher emissions. However, this redundancy provides resilience. A bulldozer that leaks hydraulic fluid or loses partial power can often continue working. The machine degrades gradually instead of failing suddenly. The contrast became stark as global emission standards tightened after 1997, following the Kyoto Protocol. German manufacturers adapted quickly by integrating advanced emissions control systems. American manufacturers lagged, struggling to retrofit older designs without compromising reliability. From 2000 to 2010, this gap widened. German machines met regulatory requirements but became increasingly complex. American machines remained simpler but faced export restrictions and compliance challenges. Precision also affects operator behavior. German machines assume disciplined operation within defined limits. Automated systems intervene to prevent misuse, sometimes shutting down machines entirely. American machines assume misuse will happen and are built to survive it. On chaotic job sites, especially during disaster response or military operations, this assumption matters. During U.S. military operations in Iraq and Afghanistan from 2003 to 2014, American-built equipment dominated not because it was efficient, but because it was repairable under fire. German-designed systems performed well in support roles but struggled when maintenance infrastructure collapsed. Precision lost value when logistics failed. The core issue is not whether a machine is overbuilt or overcomplicated, but whether its design assumptions match reality. German machines excel when rules are followed, conditions are stable, and systems remain intact. American machines excel when rules break down, conditions deteriorate, and improvisation becomes necessary. When precision becomes a liability, it exposes a fundamental truth. Engineering success is context-dependent. A perfectly optimized system can fail faster than a crude one when the environment turns hostile. Overbuilding wastes resources, but overcomplication risks total failure. This reveals a hard lesson learned repeatedly from 1980 to the present. The most advanced machine is not always the most effective. In the real world, resilience often outperforms perfection. Bigger, louder, stronger. America's raw power approach. Under fire. For decades, American heavy machinery has been defined by one dominant philosophy: raw power. Bigger engines, louder operation, and stronger frames became the signature of U.S. industrial equipment. This approach produced machines that could dominate massive construction sites, mines, oil fields, and military projects. It delivered results where failure was not an option. But over time, that same philosophy has come under growing criticism as conditions, markets, and priorities changed. The roots of America's raw power mindset are deeply tied to geography and scale. The United States is vast, resource-rich, and historically less constrained by space. Construction projects often stretched across open land where efficiency mattered less than speed and endurance. Machines had to operate continuously, far from cities, spare parts, or specialized technicians. In that environment, power was insurance. If something went wrong, brute strength could compensate. Manufacturers such as Caterpillar, John Deere, Case, and International Harvester built their reputations on this reality. Engines were large and conservatively tuned. Frames were reinforced far beyond minimum requirements. Hydraulics favored simplicity over finesse. The result was equipment that could be abused, poorly maintained, and still keep running. American machines earned a reputation for surviving conditions that would disable more delicate designs. This philosophy proved extremely effective in large-scale infrastructure. Highway construction, dam projects, strip mining, and agricultural expansion depended on machines that could move enormous volumes of material quickly. In these environments, fuel costs were secondary concerns. Downtime was the real threat. A machine that burned more fuel but stayed operational was more valuable than a more efficient machine that stopped working. However, raw power came with trade-offs. Larger engines consumed more fuel, generated more heat, and produced more emissions. As global awareness of environmental impact increased, American machines began to face criticism for inefficiency. What was once seen as strength started to look like excess. Competitors, particularly from Europe and Japan, promoted smaller engines paired with advanced systems that delivered similar output with less consumption. Noise became another liability. Loud machines were once accepted as a normal part of heavy industry. Over time, stricter workplace safety rules and urban construction regulations changed expectations. Equipment designed for open landscapes struggled to adapt to dense cities and regulated job sites. Power that could not be controlled or quieted became a disadvantage rather than an asset. Even within the United States, attitudes began to shift. Contractors faced rising fuel costs and tighter margins. Operating expenses became just as important as purchase price. Machines that relied purely on size and strength became harder to justify economically, especially for long-term projects where efficiency directly affected profitability. Military operations exposed both the strengths and weaknesses of raw power. American-built heavy equipment proved invaluable for rapid construction, road clearance, and fortification in hostile environments. Large engines and heavy frames allowed machines to function despite dust, heat, and damage. Field mechanics could repair them with basic tools, keeping operations moving under pressure. At the same time, fuel consumption became a strategic burden. Supplying fuel to support power-hungry equipment required constant logistical effort. In some cases, the need to keep machines running increased risk elsewhere. Power solved immediate tactical problems while creating long-term operational strain. As markets evolved, American manufacturers were forced to adapt. Engines were downsized, electronic controls were introduced, fuel efficiency became a design priority rather than an afterthought. Critics argued that these changes diluted the identity that once defined American machinery. Supporters countered that adaptation was necessary for survival in a global market. The controversy surrounding America's raw power approach is not about incompetence or outdated thinking. It is about momentum. Designs that were perfectly suited to one environment became liabilities in another. Bigger engines guaranteed performance, but they locked machines into higher operating costs. Louder operation signaled strength, but conflicted with modern standards. Stronger frames ensured survival, but reduced efficiency. Ultimately, America's raw power philosophy worked because it matched its reality. When that reality changed, the weaknesses became visible. The debate today is not whether power matters, it clearly does, but how much power is enough and when it becomes excessive. This chapter highlights a central tension in heavy machinery design. Strength delivers reliability, but unchecked power creates new vulnerabilities. In a world shaped by regulation, efficiency, and logistics, raw force alone is no longer the final answer. Maintenance nightmares, the hidden costs, no one talks about. When heavy machinery is advertised, the focus is almost always on power, efficiency, and performance. What is rarely discussed, yet often determines success or failure, is maintenance. Behind every impressive specification sheet lies a reality of downtime, repair costs, spare parts, and technical dependency. This is where the differences between German and American heavy machinery become most controversial, and where hidden costs quietly destroy productivity. German heavy machinery is often praised for reliability, but that reliability is conditional. It assumes correct operation, scheduled maintenance, and access to proper service infrastructure. German manufacturers design machines as integrated systems, where engines, hydraulics, electronics, and safety mechanisms are tightly linked. When everything works as intended, maintenance intervals are predictable and wear is minimized. However, when something goes wrong, the consequences can be severe. A common criticism from operators is that German machines fail cleanly but completely. A single sensor fault, software error, or calibration issue can trigger automatic shutdowns designed to protect the system. From an engineering perspective, this is logical. From an operational perspective, it can be disastrous. A machine that is mechanically sound may be rendered useless because a warning system cannot be cleared without specialized tools or authorization. This creates dependency. German equipment often requires manufacturer-approved diagnostics, proprietary software, and certified technicians. In developed regions with strong dealer networks, this model works. In remote construction sites, mines, or disaster zones, it does not. Waiting days or weeks for parts or technicians turns minor faults into major delays. Maintenance costs increase not because parts are failing, but because access is limited. American heavy machinery approaches maintenance differently. Simplicity is treated as a form of reliability. Systems are designed to be understood, accessed, and repaired quickly, even imperfectly. Components are often standardized, allowing mechanics to substitute part, improvise fixes, and keep machines operational despite unresolved issues. Maintenance is not about perfection. It is about continuity. This philosophy results in machines that tolerate wear, leaks, and partial failures. Hydraulic systems may lose efficiency, engines may run rough, and frames may show stress, but the machine keeps working. Maintenance becomes gradual rather than disruptive. Operators often accept reduced performance in exchange for uptime, especially on time-sensitive projects. The hidden cost, however, appears over time. American machines typically require more frequent servicing, consume more consumables, and experience faster long-term wear. What they save in downtime, they often spend in fuel, parts, and labor. The cost is spread out and less visible, making it easier to justify in the short term but expensive over the life of the machine. German machines invert this equation. They often have lower routine maintenance and better efficiency, but when failure occurs, costs spike sharply. A single electronic module or emissions component can cost as much as several mechanical repairs on an American machine. The unpredictability of these failures makes budgeting difficult, especially for contractors operating on thin margins. This contrast became especially visible during global supply chain disruptions around 2020, when access to specialized parts and technicians became uncertain. Operators with complex, electronics-heavy machines faced extended downtime, while simpler equipment remained operational through local repairs. Maintenance philosophy suddenly became a strategic issue, not just a technical one. Training is another overlooked cost. German machines assume skilled operators who understand system limits and warning indicators. Improper use increases failure risk dramatically. American machines assume misuse will happen and are built to survive it. The cost of training, supervision, and compliance is therefore higher for precision-focused equipment. Neither system is inherently wrong. The problem arises when buyers focus on purchase price and performance while ignoring maintenance realities. A machine that is cheaper to operate per hour can become more expensive per project if downtime is frequent. A machine that never shuts down can quietly drain budgets through fuel and wear. Maintenance nightmares are rarely dramatic. They appear as delays, missed deadlines, idle crews, and unexpected invoices. These costs rarely make marketing materials, but they shape real-world decisions more than horsepower or efficiency ratings. In the end, the true cost of heavy machinery is not measured when it is running perfectly, but when it stops. And how a machine fails, suddenly or gradually, often matters more than how powerful it is. Efficiency versus durability. Which machines fail? First, under pressure. The conflict between efficiency and durability sits at the center of the German versus American heavy machinery debate. Both sides claim superiority, yet real-world pressure exposes uncomfortable truths. Machines are rarely tested in ideal conditions. They are pushed beyond design limits by deadlines, poor terrain, human error, and unexpected failures. Under those conditions, efficiency and durability stop being abstract concepts and become deciding factors in whether a project succeeds or collapses. German heavy machinery is engineered around efficiency as a core principle. Engines are optimized to deliver maximum output with minimal fuel consumption. Hydraulic systems are finely tuned to reduce waste and improve control. Components are designed to operate within narrow tolerances, minimizing friction and wear when used correctly. On paper and in controlled environments, this approach delivers impressive performance. Machines do more work per unit of fuel, generate less heat, and experience slower degradation when maintained properly. However, efficiency depends on stability. German machines assume predictable operating conditions, disciplined operators, and consistent maintenance. When those assumptions hold, efficiency becomes a strength. When they break, efficiency can turn into vulnerability. Systems designed for precision often lack redundancy. If one component fails, the entire system may be compromised. Failure is not gradual. It is abrupt. Durability, by contrast, defines the American approach. American heavy machinery is built with excess capacity. Frames are thicker, engines are under-stressed relative to their size, and systems are designed to tolerate abuse. Efficiency is sacrificed to ensure that machines continue operating even when conditions deteriorate. Leaks, vibration, misalignment, and overheating are expected, not avoided at all costs. This difference becomes critical under pressure. On job sites where timelines slip and workloads increase, machines are pushed harder than intended. German machines respond by protecting themselves. Automated systems reduce output or shut down to prevent damage. From an engineering standpoint, this prevents catastrophic failure. From an operational standpoint, it halts progress when time matters most. American machines respond differently. They allow damage to accumulate. Performance degrades, fuel consumption increases, and wear accelerates, but work continues. Failure is delayed rather than prevented. This approach keeps projects moving, but transfers risk to the long term. Components may survive today only to fail later, often with higher cumulative costs. Pressure also exposes differences in how machines handle imperfect inputs. Poor quality fuel, contaminated hydraulic fluid, and inconsistent lubrication are common realities outside ideal environments. Efficient systems are sensitive to these variables. Minor contamination can cause significant performance issues. Durable systems are less sensitive, but they pay for that tolerance through inefficiency and faster overall wear. The question of which machines fail first depends on how failure is defined. German machines often fail suddenly but cleanly. A shutdown occurs before major mechanical damage, preserving the integrity of expensive components. American machines fail slowly and visibly. Operators notice declining performance, but continue working until repair becomes unavoidable. This distinction matters most in high-risk environments. In disaster response, remote mining, or military support operations, downtime can be more damaging than mechanical wear. A machine that protects itself too aggressively may fail the mission, even if it preserves its internal systems. A machine that keeps running despite damage may complete the task but shorten its usable life. Efficiency also affects logistics. Efficient machines reduce fuel demand, which lowers operating costs and logistical burden. This advantage becomes significant when supply chains are long or unreliable. However, when efficiency relies on complex systems, logistical simplicity is lost elsewhere. Specialized parts, diagnostics, and trained technicians become just as critical as fuel supply. Durability simplifies logistics differently. Spare parts are often interchangeable, repairs are less specialized, and improvisation is possible. Fuel consumption increases, but operational flexibility improves. Under pressure, flexibility often outweighs optimization. The contrast became especially visible during large-scale infrastructure and emergency operations following 2010, when machines were deployed outside their intended environments. Efficient equipment delivered excellent results early but struggled when maintenance schedules collapsed. Durable equipment absorbed abuse and remained operational, even as efficiency declined sharply. Neither approach is universally superior. Efficiency excels when systems remain intact and discipline is enforced. Durability excels when chaos dominates and control is lost. Failure under pressure is not only about design quality, but about how closely reality matches engineering assumptions. Ultimately, machines do not fail first because they are efficient or durable. They fail first because they are used outside the conditions they were built for. The true challenge is not choosing between efficiency and durability, but recognizing which type of failure a project can afford and which it cannot. Regulations, terrain, and war zones. Why design choices spark controversy. Heavy machinery design does not exist in a vacuum. Every machine is shaped by the rules it must follow, the ground it must cross, and the environments where it is expected to survive. This is why German and American heavy equipment often perform brilliantly in one setting and poorly in another. Regulations, terrain, and war zones expose the assumptions behind engineering decisions and turn design choices into sources of controversy. Regulation is the first dividing line. German manufacturers operate within some of the strictest industrial rules in the world. Environmental standards, safety requirements, and emissions controls heavily influence design priorities. Compliance is not optional, it is foundational. As a result, German machines integrate safety systems, emissions controls, and automated monitoring directly into core operations. These systems protect operators, reduce environmental impact, and ensure legal compliance, but they also add layers of complexity that cannot be ignored. American manufacturers historically faced fewer regulatory constraints, especially in heavy industry. This allowed greater freedom in engine size, noise levels, and system design. Machines could be optimized for performance rather than compliance. While regulations have tightened over time, the legacy of this freedom remains embedded in American equipment. Simpler systems, fewer automated shutdowns, and more mechanical control continue to reflect design priorities shaped by earlier regulatory environments. Terrain creates the second major fault line. German machinery is often designed for compact spaces, paved access roads, and well-prepared job sites. European geography demands machines that can operate efficiently in tight urban areas, mountainous regions, and interconnected transport networks. Precision and control matter more than brute strength. Stability, maneuverability, and predictability are essential. American terrain tells a different story. Vast open land, deserts, forests, and remote industrial zones demand machines that can travel long distances and operate without immediate support. American machines are built to cross uneven ground, endure extreme temperatures, and continue functioning when conditions deteriorate. Size and strength compensate for unpredictability. Where German machines avoid stress through control, American machines absorb stress through mass. Controversy arises when machines are used outside their intended terrain. German equipment can struggle on poorly prepared sites where vibration, dust, and uneven surfaces overwhelm sensitive systems. American machines can appear wasteful or clumsy in dense urban environments where noise, emissions, and size become liabilities. Each design excels at home and invites criticism abroad. War zones amplify these differences. Military and post-conflict environments combine regulatory collapse, extreme terrain, and constant risk. Machines must function without reliable infrastructure, stable power supply, or predictable maintenance. In these settings, design philosophy becomes a matter of survival rather than efficiency. American heavy equipment has traditionally dominated combat and disaster environments because it tolerates abuse. Mechanical systems allow field repairs. Damage does not immediately stop operation. Large engines compensate for poor fuel quality and environmental stress. This resilience has proven valuable when timelines are unforgiving and conditions are hostile. German-designed systems, by contrast, often assume regulatory compliance and controlled operation even in military support roles. Safety systems and automated protections can limit effectiveness when rules no longer apply. Machines may shut down to prevent damage at moments when continued operation is critical. What protects equipment in peacetime can hinder it in conflict. Yet, this does not make German design inferior. In stabilization, reconstruction, and peacekeeping operations, efficiency and control regain value. When infrastructure is restored and supply chains stabilize, machines that minimize fuel use, emissions, and wear become strategic assets. The controversy stems from mismatched deployment, not flawed engineering. Another source of debate is procurement policy. Governments and corporations often purchase equipment based on regulatory compliance or cost projections rather than operational reality. Machines optimized for one environment are deployed in another, creating performance gaps that fuel criticism. Engineers are blamed for decisions made far from the field. The deeper issue is that design choices are context-driven. Regulations push manufacturers toward compliance. Terrain pushes them toward adaptability. War zones strip away assumptions and expose weaknesses. When these forces collide, no design can satisfy all demands simultaneously. This chapter reveals why debates over German and American heavy machinery remain unresolved. Each system reflects the pressures that shaped it. Controversy arises not because one approach is wrong, but because machines are judged outside the environments they were built to master. In the end, regulations define legality, terrain defines capability, and war zones define resilience. Design choices spark controversy when users forget that machines are products of their context, not universal solutions. Which system breaks down in the real world, and why it matters? When German and American heavy machinery are compared in brochures, test facilities, or controlled demonstrations, both systems appear formidable. The real difference only becomes clear when machines are pushed into environments where plans fail, conditions deteriorate, and support systems collapse. In the real world, breakdown is not a hypothetical risk, it is inevitable. The question is not whether machines fail, but how they fail, how quickly they recover, and what consequences follow. German heavy machinery is designed around system integrity. Every component is expected to function within a tightly defined range, supported by sensors, safeguards, and automated controls. When conditions remain stable, this approach delivers consistent performance, lower operating costs, and reduced wear. However, real-world environments rarely remain stable for long. Once conditions drift outside design assumptions, the system's strengths can become weaknesses. In practice, German machines tend to break down decisively. A fault is detected, protections activate, and the machine shuts down or limits operation. From an engineering standpoint, this prevents cascading damage and preserves expensive components. From an operational standpoint, work stops immediately, crews wait, timelines slip, costs accumulate. The machine is safe, but the project is not. American heavy machinery breaks down differently. Systems are looser, tolerances are wider, and automated intervention is limited. Instead of shutting down, machines continue operating in a degraded state. Power drops, fuel consumption rises, and components wear faster, but progress continues. Failure is delayed rather than prevented. This approach accepts damage as the cost of momentum. This difference matters most when support systems fail. In remote construction sites, disaster zones, or unstable regions, access to diagnostics, spare parts, and trained technicians cannot be guaranteed. A machine that requires specialized tools and authorization to restart may remain idle even when it is mechanically intact. A machine that can be repaired imperfectly, but immediately often becomes more valuable, even if it suffers long-term damage. Real-world breakdowns are rarely caused by a single factor. They emerge from combinations of poor fuel quality, operator fatigue, environmental stress, and logistical disruption. Precision-based systems are sensitive to these variables. Durability-based systems absorb them. Neither approach eliminates failure, but they distribute risk differently across time. The consequences extend beyond the machine itself. Downtime affects entire crews, subcontractors, and supply chains. Idle labor costs accumulate quickly. Delayed completion triggers penalties. In some contexts, such as emergency response or military support, delays carry human and strategic costs that outweigh equipment preservation. In these cases, a machine that keeps moving is often preferred over one that protects itself. This does not mean American systems are superior. Long-term consequences matter. Machines that operate while damaged accumulate hidden costs: accelerated wear, reduced lifespan, higher fuel consumption, and eventual catastrophic failure. These costs are often deferred, appearing months or years later as major overhauls or early replacement. German systems, by shutting down early, avoid these outcomes, but at the cost of immediate disruption. Why this matters is ultimately a question of priorities. Projects with strict regulatory oversight, predictable schedules, and stable infrastructure benefit from systems that prevent damage and optimize efficiency. Projects defined by uncertainty, urgency, or instability benefit from systems that tolerate failure and continue operating. Problems arise when decision-makers assume one model fits all conditions. Procurement decisions often ignore this reality. Equipment is selected based on specifications, compliance, or short-term cost projections rather than breakdown behavior. When machines are deployed outside their intended context, failure is blamed on design rather than mismatch. Engineers are criticized for outcomes driven by deployment choices they never controlled. The real-world lesson is uncomfortable but clear. No system is universally resilient. German machinery prioritizes system preservation. American machinery prioritizes task completion. One breaks down to protect itself. The other breaks down slowly to finish the job. Both approaches are rational responses to different assumptions about risk. The reason this matters is not technical. It is strategic. Understanding how systems fail allows planners to choose the right tool for the right environment, rather than expecting perfection everywhere. In the end, the question is not which system breaks down first. It is which breakdown a project can survive.